first of 2 PowerPoints for the day. All right. So let's drag this down here. Wave interference. This is a shorter PowerPoint. Hello, that's not projecting on the screen that I want it to. That's fascinating. We can just do it here, I think. Monitor. There it is. Awesome. Okay, so wave interference. So one of the things that we need to be concerned with or need to start thinking about is we need to start thinking about, okay, what happens when two waves come into contact with one another? Especially when we think about oceans and fluid dynamics, that becomes an increasingly important topic of conversation when we're looking at the safety of people and the safety of individuals. Kaylee, in her engineering degree, she has taken now, I think, 2 fluid dynamics classes. She loves them, but she says they're also quite difficult. Looking at how water interacts or how fluids change based on the medium that they're a part of or based on the container that they're a part of. There's some really, really interesting science involved with waves, but also specifically with fluids as well. So, in terms of wave interference here, the principle of superposition states, very confusing language, but when 2 or more waves pass through each other, the resulting disturbance at a given point in the medium is found by adding the individual displacements each wave would have caused. So there are 3 different types. There's constructive interference, destructive, and total destructive. This is my personal favorite name for a property of all time. Whoever came up with that, excellent work. Total destructive interference, I think that's pretty hilarious. This is what constructive interference looks like. So the displacement of a medium that occurs when 2 interfering waves have a displacement on the same side of the midline. I think this picture speaks a lot louder than any of these little words, jot points say up here. So we have wave A and wave B coming towards each other. We want to look at what happens when those 2 are going to collide. So when they collide, A and B are going to add up together. So this is constructive, in other words, meaning the other word that I use sometimes is that these are additive waves. So we take additive, yeah, I spelled that correct. You take the 2 waves, you just add up their heights, you add up their amplitudes, and that is the resulting crest here. The resulting wave is A plus B. And then after that, they just pass through each other. It's a little hard to talk about that without showing you. So this is one of the PhET simulations. I have a fixed end selected here. I'm going to manually do this because I want to create 2 different waves. And I have it set to slow motion just so we can do this a little bit more efficiently. So here's my first wave. And if I do an opposing wave like this, what we should see at the moment those 2 collide is those 2 waves, this one reflected back on the bottom side. Remember, that's what happens with fixed end. Those 2 waves are going to add together and get really big, whereas the individual waves were quite a bit smaller. You can see the size of those waves there. So I'll do that again. Let's restart that. So no, really? Stop. What can you see? The Discord? What? Okay, let me fix this. Okay, hold on, because this is super exciting. I'm talking to myself, and that's just embarrassing now. Okay, can you see that? If you click on that. Or is it just not working at all? Oh, it's 2 people messaged at me. Oh, man. That's embarrassing. Okay, sorry, folks. That's really embarrassing. Oh, I know what happened. That's why. Okay, my bad. I had clicked on the wrong thing, obviously. Can you guys see this, the wave now? Is there anyone that can't? Oh, okay. Okay. Sorry, I missed the message in the group chat. That's my bad. Okay, back to what I was talking about. Oh, man. Now, do I have to start the PowerPoint again? Like, did we miss all of that? Oh, shoot. Okay, back to the beginning. So this right here, this is a wave. And Kaylee has been, I'm just kidding, I'm not going to start that far back. So there's 3 types of interference, like I said, constructive, destructive, total destructive. Sorry, my bad, everybody. But basically, what I showed or what I talked to myself about, wow, what a lame circumstance. What I talked to myself about was these 2 waves, A and B, they come together and they just add up. Their amplitudes get this high. You just add the height of the A, height of the B together. You get an additive wave, and then they'll pass through each other. Okay, we're going to try this again. I'm going to very closely monitor Discord to see if it doesn't work. This is the PhET simulation. Again, fixed end, manual, and then I'm going to just flick this myself. But here's our first wave. If I normally did this wave, what you would see is you would see it reflect along the bottom. because we're dealing with a fixed end. So I'm going to create one wave like this, and I'm going to create one wave like this. And what we should see is that when this wave reflects, they add on to each other and get bigger than each individual wave was. So you can see that those waves are quite a bit smaller individually by themselves. So that's what happens when two waves, and let's start with a downward facing one and then an upward facing one like this. So you'll see these two waves jump up together and add together at that really high point. That's constructive interference that's occurring there. Super sorry about that, folks. That is very awkward. Also, not the first time I've done that. Okay. Destructive interference. So this is what happens when a crest meets a trough or vice versa. These are going to reduce the overall size of these waves. So if I do a top-facing wave, that was sloppy. So if I do a top-facing wave, it's going to reflect along the bottom as a trough. So I'm going to do one top-facing wave and a second top-facing wave. And we're going to see it get really, really small in the middle here where they kind of neutralize each other out. None. And let's do another one. So we'll have to wait for this wave to pass. But when these two do, it jumps to the middle and they don't get very large. That was not very clean. Let's try that again. There's one. Here's a second wave. And we'll see them kind of neutralize each other in the middle for a very brief second. They're very low on both sides. That's what a destructive interference looks like. So this green line, it's kind of tough to see here, but this is the additive of the red and the blue. The blue is clearly a bigger wave, and so that means that the resulting wave will be this green one where it's facing downwards because this blue wave carries more energy than the red wave does. Okay, total destructive interference. This is the last one. This is where the displacement of a medium that occurs, these two waves are going to collide with each other, and at their point, these two are exactly equal waves. And because they're exactly equal waves, they're going to just cancel each other out. It's like adding a positive wave and a negative wave, or like, let's say that this amplitude was +6, this amplitude of A was -6. Overall, it would be 0. So that's what a total destructive interference looks like. I think this was the only one on your assignment that I didn't ask you to demonstrate, and that's because it's almost impossible to catch it like this. It's almost impossible to get the, I didn't do that correctly, but get the total destructive interference. It's really tough to get it to neutralize with each other. I want to do one of those and one of those, and we'll see. That one's slightly bigger. So it's really tough to get these two waves to it was close there, but they didn't totally neutralize each other. There was still a little bit above the midline there. So that's the one I didn't ask you to demonstrate. There are some cool videos. I do recommend you watching them. I'm not going to play them for you here. That seems like not a great use of time for me to show you a video. Yeah, I don't know. It just didn't seem like a great use of time to me. So that is a video that you could watch. It goes through and it shows you with a slinky on the one, and then a different tutorial that just walks through each of the different waves that we've talked about thus far. But I wanted to get to this second PowerPoint here today, which is the diffraction and refraction of waves. Just check, everything's working. Awesome, cool. So diffraction and refraction of waves. So there's two different terms that we need to learn. The first one is going to be the diffraction of waves, and that's a change in direction or bending of waves as they pass through an opening or around a barrier in their path. So this is lights hitting some sort of wave, and then they have to change direction as a result of something getting in their way. And so the idea with these diffraction of waves here is that the wavelength, the smaller the wavelength, the less the diffraction will occur. In other words, if there's less stuff hitting, if the wavelength is smaller and there's more hitting the object, it will diffract less. You can think of it being like, what's a really good example here? Something very, very small. It has not a lot of opportunity to be influenced. But if we have a larger wavelength here, that means that it will diffract more. In other words, there's less of it hitting, and the wavelengths are so long that they can be impacted a lot by it. I'm trying to think of a really good example by it. Think about it this way. You have a really tall building and a really short building. The really tall building, if that were to fall over, it would take a very long time for it to fall over and it would create a huge disaster. A short building, if that were to fall over, that would fall over in a very quick period of time and it wouldn't make much of a mess everywhere and it wouldn't explode into a million pieces as opposed to the really, really tall building. I don't know. That's not a great metaphor, but that's the comparison that I'm using today. Uh, this one is kind of a more, I think this one's a more relevant example. It happens quite frequently, and this was also a huge area and still is a huge area of study in terms of looking at the travel of light, sound, the travel of electrons as well. Trying to decide if it travels as a wave or a particle. But this slit example is a really, really important example for us. So opening in a barrier, these are often called slits. The smaller the opening, the greater the diffraction. In other words, there's very, very little of whatever this wave is, there's very, very little of it that can travel through there. Once it does get through there, it wants to escape everywhere it possibly can. It's not going to keep traveling along in that straight direction that it was. It's going to try to go wherever it can. Whereas here, there's a lot more opportunity for very straight lines of waves, whatever those waves are, radio waves, light waves, sound waves, etc. It won't diffract as much. And then this is just showing what can happen if there are multiple slits in an object. So for example, if there's multiple slits in an object, light gets reflected through there or sound gets reflected through there. And at this point here, this is where we have constructive interference, which is where two crests are meeting. So this area here, if it was sound traveling, that would be the loudest area that you would be able to sit and hear most clearly. Or if it was light traveling, let's say this is light traveling through your blinds. There is an area right in between a blind where the light is going to be diffracting and concentrating because there's two different light rays meeting each other, causing constructive interference, and it'll be brighter at that one point. You can try that with your blinds. If you go very, very close to your blinds, you'll notice that if you stand, so my blinds look like this in my bedroom. There are a bunch of just rectangles like this. If you stand and you put your eyeballs right here at this one, and you get right up close to this middle one, all of the light is diffracting and it's causing constructive interference right at this blind, whatever that one is. And obviously that would continue for every single other blind, but it'll actually be brighter at that location than it will at a location 5 or 10 meters away. So that's kind of interesting. Refraction, this is the second term that we need to know. This is a change in the direction of waves as they pass from one medium to another, or of water waves as they counter a depth change. And you can actually see this in the oceans, and it's a little bit more clear sometimes in rivers where there's very obvious differences in the depths of the water. So as waves enter a new medium with differing properties, the velocity will change. So in essence, what's happening here is these waves that are really, really in some deep water, they'll have a huge wavelength and separation between the waves. Whereas where it gets shallower, the waves become a lot more concentrated. Where that's most evident in day-to-day life is if you go to a beach of some sort. The further you get into the water, the less frequent the waves will actually hit you. So if you're standing in the middle of a lake, you will not get hit with as many waves as if you were standing on the shore of the lake. And that's because those waves will come at shorter wavelengths and a higher frequency. If you've ever tried to run into a lake and jump over the waves as you're running into the lake, as you get further and further in, you do less and less jumps. This is also really interesting because when you look at, say you go to West Edmonton Mall and you go to the giant wave pool there, if you're one of the ones at the very, very front, you're going to get hit with the most powerful waves, but the frequency of those waves will not be, they won't be coming very frequently. You'll have a gap to pull yourself up in your tube and prevent yourself from drowning. Whereas if you go further and further back, you'll be hit with weaker waves, but you'll be hit with more waves at one time. So there's a really good, there's a location that me and my friends, when we went to Edmonton, we would sit there. It was like right adjacent to the lifeguard, and you would get hit with enough waves that it would push you all the way back to the very start of the wave pool. So at the very, very shallowest end. That's how many waves were constantly hitting and pushing you along. So that's just kind of a fun little piece of information there, I guess. One of the key things, though, here that we'll talk about in a sec is the velocity of those waves versus the wavelength. So this was our universal wave equation, which was velocity is equal to the frequency times the wavelength, or lambda, as we called it. The waves are from the same source, so the frequency is constant. If the wavelength increases, v must increase, and vice versa. If the wavelength decreases, the velocity must decrease, and vice versa. So going back to my West Ed example, you're being hit with more waves, not because the frequency is decreasing, but because the wavelength of those waves is decreasing. Now, the other thing that I said was if you're at the very, very front of the wave pool, so you're right where the waves are coming out, you're getting hit with really hard waves, but not a lot of them in a row. So their velocity is really high and their wavelength is really high, but the actual frequency of them remains lower. If you go further and further back into the wave pool, the wavelength is decreasing, and as such, the velocity of those waves is also decreasing. So you're getting hit with more waves, but they're going slower. It's kind of the overall idea. And that relationship comes back to this one here, that the initial velocity and initial wavelength are equivalent to the initial velocity, or the final velocity and the final wavelength. So those two ratios must be equivalent to one another. So the one calculation from this PowerPoint is that a water wave has a wavelength of 5.0 centimeters in a shallow section of water. It encounters a depth change, and its wavelength increases to 8.0 centimeters, and its velocity increases to 2 meters per second. What was its original velocity? The first step, as you probably have noticed already, is that those are both in centimeters, and our velocity is in meters per second. So instead of changing meters per second, we're going to change both the 8 and the 5 into meters, and we end up with these two values here. Again, just dividing by 100. There's 100 centimeters in 1 meter stick. The next thing is just identifying our variables. If we were in class, generally what I do when I'm marking is this step here is usually worth a mark. So I will give you units that are inconsistent and ask you to change it. And this is relevant for next year if you are taking science. Either chemistry or physics, I suppose, would be the most relevant. But your first mark will be converting your units. The second mark will always be, have you identified your variables? Have you correctly said, this is the initial velocity, this is the final velocity, etc.? And then the last step would be, or the last couple of things of marks would be, this would be a mark here. And then working through it, usually the work itself is a mark, and then the actual answer itself is also a mark. So that question would be worth 5 marks. But what we do is we plug in each of the values that we know. We knew the wavelength initial, the velocity final, and the wavelength final. And so all that we have left to solve for is this VI. And you can multiply both sides of this equation by 0.050. And when you do, you end up with an initial velocity of 1.3 meters per second. All right.